102 or something. Remarkable person. CRO, please, young people read about him. In ISI Calcutta, this work was done when he was 23. Kramer Rao inequality. So Mayuk did his PhD from Hyderabad University, and now he is the R&D head of ABB, Asian Brown Boveri, a very big multinational company headquartered in Switzerland. He has, apart from pure research, about which I can attest that he has enormous amount of energy. I started really interacting with him since last 2-3 years, and we have written quite a good number of papers, fighting with the referee, always ultra-modern. For example, at the forefront of area of research, AI, machine learning, Hamiltonian network, Lagrangian network, and picks up and trains students well, mentors them. He has PhD students from IIT Hyderabad, and in fact from IIT Kanpur also, and one of my students from here is associated with him. So please, discuss with him in free time, because there are many more opportunities for people who are interested in machine learning, AI, and those kind of things. So today I request him to chair, and Anindita, he will tell you what I just add a few lines, because I know her, quote unquote, since her childhood in quantum information theory. One way, she's a remarkable physicist, and quite a remarkable person in terms of her achievement at the cultural front, family, taking care, private new company. There before that, starting experiment in Bose Institute, which is taking shape to be a center soon, and then now CDAC. So informally again, please discuss with her later on. And she is a physicist, quantum computer scientist, and at the forefront, quote unquote, in the business world also. So now the stage is to Mayuk. Mayuk, please take care.
Okay, so good morning, you all. So thank you, sir. It's my pleasure to chair this workshop session of QIQT 2022. I have a bad throat, so excuse me for that. Little bit of cough and cold from that. So thank you so much for your kind words, and also it's a pleasure chairing this session for QIQT workshop on quantum computing and quantum information. So this is the most fascinating area of the research in the computing domain, because there is a paradigm shift that's happening in the industry, where most of the computations, the industry is working on the future of the computations, the computation for the next century or next years to come. So if you see all the top tech companies like Amazon, Microsoft, IBM, name any of these top companies. So they are working on a lot on quantum computing, quantum information, and quantum machine learning. So that's very encouraging for the students to actively participate in this research and understand the domain and work towards different research topics. And I'm very much thankful to IISER Kolkata, especially Professor Panigrahi for his for spearheading such sessions year over year, so that we could train a lot of students in India and bring ATPA to the global equality on this research domain. So with that motivation, I have a wonderful speaker here with us, Dr. Anindita Banerjee, who was the research head and vice president in QNU Labs Private Limited, Bangalore, is mostly working on quantum cryptography and quantum information security. And currently the scientist in CDAC, and she had obtained her PhD from JP Institute of Information Technology, and have a lot of industry exposure to quantum information and its security and quantum computing. So So with that little brief about her, without further taking your time, I would request Dr. Anindita to share her thoughts that would probably enlighten the students and the audience. Over to you, Dr. Anindita.
Thank you for the kind words. It's my honor, and I really love being, in a place where you get to interact with so many students. And I think I have a lot to share with them, and I'm looking forward for their participation in both the verticals of quantum, which is quantum computing and communication, as you will see in these slides. I didn't have too much of time to work on them, but I think you will get the message, and you'll have an idea of how we are planning the activities in CDAC. And when I'll hear from you and how we can work together, that'll be very nice. So as I begin, is my slide changing? Oh, yes. But I think it's, are you able to see the entire screen, or some portion of it is not visible?
Yeah, a little bit on the left side of the screen.
So how do I take care of it? Because I'm sharing it. So let me share it once again, because I don't want you to miss out on anything. Okay, maybe I'll just share the screen if that helps. No, it's... I think this is good.
Yeah. Yeah, probably you could increase little size of the slide and then proceed. Yeah, it's I think.
Okay. Okay. So this is good, right?
Yeah, I hope for me, I hope for yeah.
Okay, so let me begin. So I'll be doing mostly the talking, and I have very little content on the screen. See, when we're talking about quantum technology, we're talking about different verticals. One is quantum simulation, the other is quantum computing, then quantum communication, quantum cryptography, sensing, and metrology, right? And why do I venture out in these domains? It is not going to substitute the present way we are seeing the world, but it is going to give you an add-on. It is going to give, you're going to leverage on certain aspects. Like, for example, it will increase the precision of the current measurement technology. It will increase the effectiveness in different verticals, in different application areas. Then, of course, the cryptography part, we all know about it. So it is going to be take care of future quantum attacks. Then new capabilities that were beyond the scope of present technology. Now, all these solutions, whether it be software or it be hardware, they are getting evolved, they are getting evaluated. But then certain parts of these products are already there in the market. And if we categorize them in terms of technology readiness level, then based on certain papers and also NIST, I have shown this TRL level and also the expected time frame. Having said that, we know there are certain devices, for example, quantum key distribution, quantum random number generator is already there, and it needs to be evaluated, and rigorous testing has to be done. The testing methodologies has to be looked into, benchmarkings has to be done. So this is the global picture. Now, and it gives you a sense of requirement, right? That why it is interesting. Then let us go into the global highlights. This slide is about quantum computing. So we know Enel, which is a multinational energy company. Now they worked on quantum solution to identify an optimal plan for assigning maintenance work to teams. Then in rail transport, they also attempted, it was in Tokyo, and they made it possible to achieve the best and the most efficient combination for simultaneous arrival of different trains. So these are the different, I would say, POCs they have done to see how to leverage the quantum solution in terms of computational capability. Then BMW had collaborated with Honeywell to boost the supply chain efficiencies. So everybody is exploring, you see. Then even the Volkswagen with D-Wave. So you will see a company, a user company and a hardware company coming together with a solutions team, and they're trying to do a POC to address or to show to the world how this quantum is going to give an advantage, maybe at a particular time, not at present, but in a particular time frame, when we say that mostly 2025 to 2035, where you'll have some fault tolerant quantum machines, as predicted by the McKinsey report on quantum technology. Now let us go to communication side. In 2016, our neighbors started working on this quantum free space communication, satellite communication. Then we have, and they have done quite a lot of work in cryptography, so fiber-based free space, and they are working on applications. So one is the science part, and the other is how the science part is helping the community. So different applications were demonstrated. A backbone fiber link is established. Then an attempt for an integrated network, quantum network, is also taking place. And there are few players, in the game. And now let us look into the national scenario. We know that in 2019, 18-19, Quest was there, and they had, government had given some 80 crores, particularly to develop a quantum computer. Then there was this national mission on quantum technologies and applications. Now CDAC is also going to be a part of it. And very soon in the next year, just like CDAC has national supercomputing mission, quantum mission is also going to get launched. And for that, we are working out the roadmap of what needs to be delivered and will be, will be viable when this project or this mission comes to an end. So we are rigorously working on the roadmaps and trying to build partner with industry and startups. Then there is this iHub, which came out from this NMICPS, and also in CDOT, I think they have, CDOT is a sister agency, and they have done quantum communication lab, where they have developed a QKD system. They have demonstrated certain applications. And they are particularly working in distributed phase reference protocols, DPS and TAO. So this is a national scenario. Now from CDAC, what we are trying to do is, it's for the first time in India that we set out an expression of interest, inviting partners, particularly in the quantum domain. Now, it's of three parts, right? One is startups. It can be a month old. Indian startups can be a month old in this technology, and we drafted it in a manner that it motivates people from coming out from research agencies to make small startups. Maybe you want to work on quantum algorithms. It needs nothing more than your brain, right? And you have cloud access, so you can work you can have startups on quantum solutions, algorithm development. If you want to contribute on the hardware part. So this is one area, the quantum startups, which can be 1 month to maybe 2 to 3 years old. Then we have industry. Maybe they have a branch who works on quantum. So what will be the legalities and technicalities around? We made it very smooth so that they can participate. Then it can be an industry outside, and they have an office in India, and they're working on quantum. Even they can apply. And even if there is a industry or a startup who doesn't have anything to do in quantum, but around quantum, like quantum assisted technologies, they are also welcome to participate. So I will suggest that and request all of you to please take a look into the CDAC website, and there you have the expression of interest. Even if you do not participate and you give me your inputs, it will help me fine tune it when we put it up again, maybe after a few months or maybe next year. So 15th July is the last date. Now let us go to, so now these are the 4 verticals. Why these are important? Because CDAC will be working in the vision of NMQT. So we have these 4 verticals: quantum communication, computation, sensing metrology. Simulation is something which we will be interested to look at also. Now, you'll have to be ready for a quiz. I have some 15 questions, which I'll give the answers maybe at the end of the session. So you can just need a pen and a paper, write your full name and make a table. There will be 50. So it should have 15 rows, 2 columns. And if you're sitting with a friend, then just write, fill in the serial number from 1 to 15 and the question will come now. The first question is, quantum computers don't really have any applications because classical computers are so powerful. True or false? Second question, in the next 10 years, classical computers will be universally replaced by quantum computers. True or false? Third question, quantum computers are expected to replace classical computers for some applications. True or false? Fourth question, quantum computers and classical computers solve problems in the same way. True or false? I'm not going to go back to these questions. So, so now I'll be going to the next slide. I hope you have answered these 4 questions. I do not have any mechanism to, or maybe in the chats, if you can write it as good, then I can proceed. Yeah, okay, I can see some numbers. So I think it should be fine. Let me move on to the next. You can stop me if you want. Okay. Now, the mission program. So when we are working on a mission, we'll be looking at capacity development. We know that there is a global crisis on awareness on quantum, be it inside certain agencies, be it inside certain some research institutes. But there is a requirement, and particularly, I think, hardware engineers, quantum hardware engineers. So this is one area which we'll be looking at. Second is, of course, the as I told you, there are certain devices already in the market, and we would want to look at it, test it, evaluate it. So if you have any ideas, or if you want to work in developing methods for testing or evaluating these products, we welcome you. So this is another vertical. And the third one is the quantum business. We want to work on the use cases. For that, we are doing a field work, going with, talking to industries, defense, strategic partners, and outside international collaborations, and trying to identify the problems, which is not very difficult because we do have a lot of content in terms of reviews, reports, and publications as well. So we have identified, and we are going to pursue it with our international partners and with our startup and EOI partners. Then towards Global Quantum India, we want to contribute, or we want to participate in the international forums and standardization processes. So this is also something which will happen gradually. But this would be the overall picture about what we want to do when we have our quantum mission, when it starts rolling. So we go to the next. So these are some of the partners we are working with, and the collaborations are ongoing. So now you can see they are in the field of communication, computing, and standardization. And I think it will take some time, but as in case of every other, this is how research happens. It's not very quick, but you will see some good work coming out of these collaborations. Apart from that, we also have platforms which I'll talk about, computing platforms, simulators, and we are collaborating with Atos, NVIDIA, and we have the access in CDAC. So if you are interested, we want people to actively utilize those platforms, particularly the students, and see how, and if you can come out with something good, or basically it'll be fun to see how the algorithms work in different simulators, different types of simulators. or what we say today is accelerator cans. So now let us talk about quantum computing. In quantum computing, we are looking at 3 particular technologies. One is superconducting circuits, qubits. Second is ion trap based qubits, and third would be photonic based. And we are working on developing control and monitoring hardware for these technologies in association with academia and startups or industry. Now, when we are looking at it parallelly, we are trying to work on creating a hybrid quantum computing system or ecosystem where we would have a quantum processor, and CDAC already has supercomputers, and we try to put these 2 things side by side and execute an algorithm. And so there are many things which needs to be developed apart from a quantum processor, particularly working on the interfaces and additional things in the software stack. So we would want to build that ecosystem. And second is, we know that there are 2 models of computation. One is the circuit model, Turing-based model, which is your simulator, gate-based simulation. Another one is the annealing. The industries we are looking for is actually the pharmaceuticals, chemicals, automotive, and finance. And we'll be taking up finance and pharmaceuticals, as CDAC has a very good group in weather forecasting and bioinformatics. So that is something will be of our immediate interest. Then we work on optimization, factorization, and any application which surrounds this quantum linear algebra, AI QML algorithms. So these are the areas where we have started working. So initial steps are being taken. Then we go to, okay, so now we talk about the simulator part. It's a general slide, when you have the classical gates, AND gate, NOT gate, any gate you take, you have a fixed number of inputs and you have one output, right? So there is into and onto mapping is not there. And this is how a gate differs from the classical and quantum. But then we can execute the same function we are doing on the classical using quantum gates as well. The truth table looks different. The maths is different. Technology is different, but the execution or the purpose remains the same. So here I showed you one example of an XOR gate, how would it be looking like, and when we do it in a using a CNOT gate, how a quantum gate, how it works. So now we say that there are some mathematical functions or problems which we make an algorithm to execute it. From algorithm, we work out the circuit, and then we try to simulate it on a classical simulator. So for the next 2 slides, I'll be talking about only classical quantum simulator, right? So we can talk about certain algorithms which can be executed only in a quantum computer and may not need an integration with an HPC system. So those can be certain, like maybe Grover's hidden subgroup problem, and trying to understand the bigger picture by executing these smaller algorithms on a smaller platform. You see the Qkd provides you around 32 qubit simulator, and there's a reason why, why we cannot extend it more to a higher number of qubits. So and that is where we absolutely say that a quantum computer will be needed if you want to do the computation, quantum computation. And we know Feynman, that we cannot simulate quantum physics using a classical simulator. So keeping that in mind, but when you're doing a computation, you need a reference, you need to benchmark. So we may need a small scale simulator, and then we see how the algorithms perform. And then we go for a QPU, compare the 2 algorithms executed in a simulator and a quantum computer, work out the error correction algorithms, work out the error mitigation problems, and then see how the results, and we are able to execute a use case. So this is the path we are going to take. So this slide just wants to talk to you about, that there are different technologies which executes a quantum processor. See, IBM, Rigetti, they are working on superconducting qubits. Then Xanadu is working on photonic. Microsoft is working on topological qubit. So there are different technologies, but when you, but finally they're executing a circuit. And when you talk about circuit, you're talking about certain parameters, how to characterize the circuits. You're looking at the number of gates, you're looking at depth of the circuit, width of the circuit. But when you're modeling this circuit in a quantum computer, the parameters change. You're talking about quantum volume, you talk about clocks when it is an IBM system, when it is an ion trap, there are algorithmic qubits. So there are different models. Benchmarking is actually happening, and I think we should get into it. And scientists from India are actually working on these systems, and I think they'll be the best persons to contribute in this direction. Then this is a QSIM, and in QSIM platform, it is actually developed. The quantum part of it, I would say, is developed by academia, by Professor Apurva Patel and his team. And how CDAC has contributed is, it is working on the classical part of it, on the front end and the back end. On the front end, there is a team in CDAC Bangalore who provides the user interface and the cloud, and there is a team in Hyderabad who works on the back end or the middle layer. Then there is another team in National Superconducting Mission, and they provide the hardware part of it, which is using supercomputers. So this is how the entire, and then we provide a cloud access for QSIM. Now it is still under a lot of improvements, and performance are getting increased. So it will be nice to see how the circuit, how this algorithms work in the simulator. It is a density matrix simulator, and it claims, that you'll be able to better simulate. You will be able to better simulate it in a noisy environment using density matrix kind of a simulator. So this is, you can do a comparative analysis of an algorithm in QSIM with respect to another algorithms in Circ or maybe in Qiskit. So again, all these platforms can be provided in CDAC. And if you are interested to execute these small, interesting assignments, you can always contact us for that. And if you have certain observations about the simulator, and you suggest certain improvements, you want to get into the maths behind it, nothing stops you. We can always engage. So here we have three different models of HP supercomputers. One would be the Shavak, which is actually a mini supercomputer. So what we offer is, if you have a QSIM, the simulator, and we provide the hardware, which is Param Shavak, which is a tabletop supercomputer. So then it becomes a part of your lab. Then second is the QSIM on cloud. It is provided by Param Siddhi. So Param Siddhi is an AI-based supercomputer. And the second, then the last one is about, I think it's Param Siddhi and Param Shakti. Param Shakti is HPC based. Now we classify these supercomputers based on their GPU and CPU percentage or ratio. And based on that, you have different applications. So one of the machines is more useful in deep learning kind of an application. The other is for maybe scientific purposes. So that is how they are being, say, we take Param Shakti, which is Param Shavak, which is here, and then we provide the simulator, and it comes as a virtual, as a offline or physical lab, quantum computing lab, right? Then we go to these, yes, the supercomputers. We have a series of supercomputers, and I just mentioned to you, I mentioned Param Shavak, Param Siddhi, and Param Shakti. Yeah. So this is the reason why we are talking about building a hybrid quantum computing system. So if we procure one, and then it can be agnostic, it can be made agnostic, and we can develop the entire ecosystem around it. So this is one thing which is there in our roadmap. Now we look into the second, this is the hybrid quantum computing HP with. So if you have a quantum computer, it shows superconducting qubits, but it is not necessary. It has to be from that technology. It can be something something which is more scalable, or it can be photonic based, and we integrate that with our HPC systems and provide the hybrid computing ecosystem. And we are pursuing this this project with international partners as well. So yeah, I think I have to, let me go to the objectives. The objective is to develop hybrid quantum classical quantum computer with integrated to an HPC supercomputer, then development of hybrid quantum software stack, benchmarking and performance evaluation of hybrid quantum algorithms, and demonstration of quantum use cases. I think I've mentioned that the areas applications, and they can be much more than what it is already here. Just remember the 4 industries, and remember the 4 problems which can be solved are attempted from quantum. The industries is pharmaceuticals, chemicals, automotive, logistics, taking care of logistics, and applications. And the problems would be optimization, quantum linear algebra, factorization. Okay, so these are the 4 industries and 4 verticals which you should be looking into, and there will be so many applications coming out of it. Okay, so now we talk about okay, so the next quiz will be after a few slides. So now we talk about a photon, superposition and interference using linear optics. It's just that, we when you want to do computation with optics, then beam splitter is actually a very powerful tool, and you can realize the gates which you the gates which you see in your classical world is realized using optical passive components in the quantum world when you're working with photonics quantum computing, or it can be quantum cryptography. We use beam splitters and interferometers to encode and decode information in quantum communication part. And when we say this, it is it can be polarization encoded, it can be phase encoded. So different degrees of freedom of photon is used to encode information using these kind of optical tools. Then we go to creating a photon in superposition. Okay, so this is the maths behind it. So whatever we do in quantum is actually, there is a maths behind to show, and it is much more convincing than when you try to make somebody understand. So when you have a beam of photons, when you have multiple photons hitting a beam splitter, it actually divides. But when you have a single photon interacting with a beam splitter, then when it comes out, it is actually in superposition in both the paths, in transmitted and reflected. Now there can be different beam splitter, 1x3, 1x2. So then but there is a mathematical representation of the beam splitter, and you can use these instruments to theoretically prove that how things work out in communication and computing. So this is the interferometer. So this is again some maths behind it, which tells you if you have a single photon, then you are always detecting it at one of the detectors, how this takes place. And this is a very ideal condition. Whenever you put a phase element into it, then it kind of behaves in a probabilistic manner depending upon the phase in it. And this is how we do phase encoding and decoding, phase decoding in a quantum communication system. Based on the values of pi, you are going to get, suppose, 70% detection on one, 20% detection on the other one. Now, please understand that they will also, nothing of these optical components are ideal. There will be other parameters apart from being, like the ambient light and all. So they will all play its part, and you will never get 100% detection in one of the detector. Even the detectors are not ideal. So there is a lot to understand about the specifications, the limitations of the components, the nature of the optics which you're using a single photon states. I have particularly worked with the single photon states on generated by spontaneous parametric down conversion with Professor Shomshubra Bandyopadhyay in Bose Institute, and we have a good lab there actually in Bose Institute. So these are the things which you can always look at in Kolkata lab. And apart from that, we are also building a quantum optics lab in CDAC Pune. If you are interested to work, we'll be also happy to show you certain experiments of this kind. Okay, so this is the final state, and yeah, the maths behind these interferometers. And then let us talk about, oh, I'm very sad. The quiz has not yet come. Huh? I think I should have put it somewhere. Okay, anyway, so let's talk about portfolio optimization. This is one such application which I worked out with QKrishi. So since I was working on quantum communication domain for 4 years continuously, you know, looking nothing outside a DPS QKD and a QRNG. And so when I was working with, when I joined CDAC, it was quite a challenge because the domain is on quantum computing, and a lot had been done in this domain. There is hype, and it's very important to understand what is the hype and what is the right path to take in this direction. So the QKrishi was a wonderful experience for me. Then so I worked on this particular problem on portfolio optimization. So portfolio optimization is a core problem in finance, right? And in other areas as well. Optimization is a NP hard problem. We don't say that quantum solves it, but quantum kinds of give you near optimal solution to this hard problem. And there are other ways also where this problem is approached. But I think quantum takes you claims to take you near to it. So now you really want to understand how this works, how this problem will be useful in the quantum to an industry, basically. So since I'm in an R&D organization which interacts with industry, we take the problems for industry. So we have to convince them both in terms of money and in terms of application, you know, how to leverage this leverage quantum for their application. Now you talk about the finance industry, you will see that here they have divided this into 3 areas: low, medium, and high, the economic value. So you will see that, you know, how the finance industry, what is the status of finance industry till 25-30, maybe it is low, and it goes to medium after that. Now, if you deep dive into this particular review article, which is McKinsey report, it says that, you know, that use cases based on optimization problem is going to be there during 25 to 30. And interestingly, after 30, when you have this, when you have, I shouldn't say, when it is expected to have a fault tolerant quantum computer, then it's going to shift to QML. So QML related problems will be more interesting in finance industry. For example, risk management, credit fraud detection. So those are the applications which will be lucrative and will be actually doing some real contribution in finance. And you may be interested in this. So here you already have these applications. Yeah, good. So you already have these applications. So you can look into these, and I think it's good to deep dive into any one of them and explore applying it using the platforms which is available. So you see that the value at stake in pharma, chemical, automotive, finance, the 4 industries I was talking about, is nearly $700 billion. So when you talk to industry, you'll have to talk in terms of the advantage with respect to money, time, efficiency. So these are the aspects which, you know, they are interested. So what we did was, so here again, it says from 2022 to 2025 is an era of NISQ advantage, and the use case around optimization is going to play a bigger role. Again, from 25 to 30, it is a fault tolerant era, and particularly QML and AI is going to play a bigger role. So yeah, So now we come to the business value. One of the most promising quantum applied use case is portfolio optimization. So this is the problem we had taken, and exploration is worthwhile because of the value at stake, which could be in the range of billions of dollars. Now, when I'm writing here billions of dollars, there's a justification given and how it adds up to be billions of dollars. In the next slide, I think, yeah, the JP Morgan Chase explores quantum advantage, entered into a partnership with IBM, IBM Q, and they are exploring, and they have also done something bigger in this. Is JP Morgan Chase research team brings portfolio optimization a step closer. So when you realize this, there are different algorithms and there are different varieties of each and every algorithm which you can explore. So this is the time to explore those algorithms and see which is more time efficient, which is better suited. So those explorations and experimentations is actually happening. And this kind of a thing happens closely with a user and an R&D team, and you have the IBM or it can be any quantum hardware provider, quantum computing provider. Then you have Japan's Nomura also, and Chicago's Quantum. They actually, there are 2 or 3 papers on this group, and they actually have shown that the results from quantum QAOA and VQE, so these are variational quantum algorithms. They use these algorithms and showed that the final result or the selected portfolio is actually equal to what you get from a classical algorithm as well, state-of-art classical algorithms. And when you have a fault-tolerant quantum computer, you can actually explore, you can go explore both vertical and horizontal aspect of this application. So when we say just a little bit of brief about this modern portfolio theory, it was introduced by Markowitz, and he also got a Nobel for that. It is also known as mean variance model, and it aims to create the most return to risk. You can see the graph here. It is the most return to risk efficient portfolio by analyzing various portfolio combinations based on expected return, which is the mean, and standard deviation, which is a variance of the assets. So I don't want to get into the particular problem. We are working in collaboration with an agency on this and exploring more aspects around it. But the idea to include this in the side is this is just one of them, and we can do a similar kind of a thing with another organization and explore other use cases and see how it will help an industry. So variational algorithms, so VQ is just one of them. And again, quantum walk is actually another thing which you may want to explore, how they work as a, because they work on photonic based systems. I don't know if you have heard of Strawberry Fields Quantum, then it's a good time to explore these simulators and see how these applications or these algorithms can perform in these simulators. So yeah, just this result part that we try to solve this problem using classical approach, which is there in the Qkd, and quantum approach, VQE and QAOA, and the output, and also do it in the quantum hardware. The quantum hardware in Qkd is only 8 qubits, right? 8 qubits. So it doesn't really help if you are working on a protein folding problem or you're working on optimization problems. So that is the reason if we have a quantum processor, maybe till 20 qubits, what CDAC is looking at, 20 to 50 qubits, then, and we have this hybrid computing ecosystem, we have the simulators. We have simulators with NVIDIA and all, where you can you can put the simulators in these accelerator cans, which has different combinations of GPUs, and see how efficiently these applications run in these platforms. Okay, so there's a quiz time. So question number 5: quantum computers are expected to solve optimization problems relatively easily, true or false? Then the 6th question: quantum computers are expected to be solving compared to classical computers. These are the options, A to F. They can be multiple. Okay, but make sure you don't select the wrong ones. If you select one wrong one, then the entire thing goes wrong. Okay, it's a negative marking. Then I'm going to question 7. The best current quantum technology is the topological qubit, true or false? The existing types of quantum technology have trade-offs in terms of speed, reliability, and scalability, true or false? Then question 9, quantum computers are expected to be able to break classical encryption schemes, true or false? And the 10th question, and classical encryption schemes are based on, it can be many as well, but don't select the wrong ones. Okay, so can I proceed? Because I'm not going to go back to this page. Yeah, I think I can. I'm seeing some messages, 1920. Okay, so I'm going to the next slide. So when you're talking about now communication, so in communication, you're trying to protect. So the entire business of quantum communication is actually generation of encryption keys. We say that the communication is protected as long as the keys, which is the weakest link, keys are protected. In classical, there is no such solution. In quantum, we approach it in two manners. One is, since all the encryption schemes, they are based on mathematical problems. So we say there are certain mathematical problems which some quantum algorithms can break them in polynomial time, or they give exponential speed up. Okay, and in some it gives a quadratic speed up. So and there can be many algorithms which may or may not be published, you know, which is really something. There's a favorite quote, you know, that human genuinity cannot concoct or cannot make a cipher which human ingenuity cannot decipher. So I think if you have a mathematical way of doing an encryption or like an RSA problem, then there will be some ways also to crack it, unless you say that this does not depend upon computational security. So in classical computers, we were talking about computational security. But when we go in the quantum era, we'll talk about information theoretic security, which means, in simple words, that even if you have all the required resources, you will not be able to crack it, be it time, be it space. But in computational security, you know that this is the space or this is the power of your supercomputer. So with this speed, you will not be able to crack it for maybe some billion years. Now, when a quantum algorithm comes, they say that, okay, this problem is not solvable or will take billions of years in a quantum computer, in a classical computer, but in quantum, it will be done in you know, it will be exponentially faster. So there is a time associated and you'll be able to crack it maybe in few seconds. So this is the advantage when we say that we want quantum communication. Okay, now when we talk about in scientific world, we say quantum communication, you have a transmitter, you have a receiver, you encode information in the degrees of freedom of a quantum entity, and you say that if anybody is going to disturb that state, then or monitor it, then you're performing a measurement or some operation on that state, and its state gets altered because it's an unknown state. And you say that if this is the error beyond a particular error, then you will have then somebody is monitoring you. So then we drop the keys. So this is how we say secure communication works. We actually generate secure encryption keys for communication or for a cryptogram. There are, of course, other ways to do quantum communication, where we do quantum secure direct communication or DSCI, which means that, you know, basically you do not share the encryption keys. You do, it's a different kind of cryptography, which is very difficult to think about in the classical world without keys, right? And there's another aspect which I'm working with Professor Shrikant with in PPSIR. And it is on counterfactual based QKD. I have worked on differential phase shift QKD, and there the security was basically on non-orthogonal states. We had We used to take, just like any conventional system, it is either a single photon source or it is a entangled or it is a weak coherent source. But in these kind of protocols, which I think anybody in India would be doing right now, which is in the news, is all based on differential phase QKDs. Phase we use because it is better for communicating in fiber. If it is a free space, they'll be going for for polarization based. And what Professor Urvashi Sinha has done, what Professor in PRL RP Singh sir had done, it's based on quantum single photon states or distribution of entangled states, which has been done for a few distance, and they are actually looking at expanding that distance in free space.
Dr. Anindita, the last few minutes.
Okay.
Thank you.
Okay, so I'll just, I think I'm in the last 5 to 6 slides. I will not, so this is basically the non-orthogonal states. You have a rectilinear representation, you have a diagonal representation. Now, if you, I did this simple, experiment. If you have a red ball, which is say vertically polarized, you have a blue ball, which is diagonally right polarized, and you ask a question. When you ask this question, you actually know the state. So when you know the state and you ask the question, you already have a right answer. And in the other case, where you do not know the state and you happen to ask randomly a wrong question, then the state gets changed, which is not seen in the classical world. And this is a principle of BB84 QKD and other such QKDs, where any kind of measurement you do on an unknown state changes the state itself. And it is a measurement. So basically, it's a quantum measurement which does that. And you'll not be able to go back to that state, which the original state. And when you again do the measurements on these states, the tuber actually tells you whether somebody had changed it or somebody hasn't. So only Alice knows the questions. Eavesdropper does not know what state it is coming from. So he will be using all sorts of gadgets and quantum gadgets. When I'm saying quantum gadgets, it's basically the 3 measurements we do on a quantum channel. And the quantum computer, so that you can do a generalized measurement and you can look for coherent and the advanced quantum attacks. So the thing is simple. You do not know the state, so you do not know how to measure. You apply wrong measurements, and then you get errors and you are detected. So this is the basis of cryptography. You are asking the right question. So if you are party with Alice, then it is difficult. So there are papers. You have to understand this entire model as in where the quantum boundaries are set. Now, when you apply this algorithm in a because after all, you'll be selling it as a box, right? So there are different zones or different levels of security. So they have the different parameters, and then it makes you useful for an agency to use such a technology. So this is about the Qkd algorithm. How this works is you have an Alice and you have a Bob. So there is a quantum transmission happening. They will always be connected with a classical channel, which can be a fiber optics, or it can be internet. Okay, or it can be you just take a microphone and then you announce the results. So it's as simple as that. And quantum channel is something where you're shooting the light on a free space. Those are quantum entities, and the quantum channel can be on a fiber, it can be on a free space. Okay, so one level is which is the actual quantum part, which is the quantum transmission. And both the Alice and Bob, they have their algorithms which they run using optics and optoelectronics, and they do detection part. So that is the only quantum which comes in. After that, every step which you see is actually classical. An analysis is required which goes back to the source characterization, the leakages which happens throughout. Then you have a mathematical process to actually filter out or compress the information so that the eavesdropper does not have access to the real keys. And there is actually a lot more to it, because finally these keys will be used by the agency. So we call it something like a composable framework, where the keys generated or the output of QKD should be input to some other applications. So those structures are also worked out in QKD, and it is very interesting to see it's multidisciplinary, and people from physics, electronics, information theoretic science, mathematics, all have a role to play in this kind of a architecture. And if you are interested, even if you are from different disciplines, we'll be very happy to work on it. We are working on free space quantum communication, particularly agile quantum communication, and we are working on this, photon experiments, single photon experiments. So we'll be happy to collaborate on this aspect. Now we are coming to the final 5 questions. This is the radiation and matter have properties both of particles and waves. Is called what? Confusion, mixing, wave particle duality, and entanglement. Next question. Max Planck's great discovery was that radiation energy is emitted in packets that he called what? Gamma, wave functions, quanta, or photons? Next question. Photon. Okay, 13th question. When 2 particles are entangled and it is observed that one has its spin up, how long does it take for the other spin to be down? 1 microsecond? Instantaneously, or one nanosecond? Okay. 14th and 15th question, the last 2 questions. In Heisenberg's uncertainty principle, which 2 measurable properties of a particle cannot be observed precisely at the same time? And there are 4 options. Quiz, the last one, who is the father of quantum computing? Okay, I'm going to the next slide. That's a thank you. And now if you have partners, you can exchange the answer sheet and evaluate the marks. Okay, so there goes the answers. I'm going to be here just for 5 to 6 seconds. Yes, and you can send me the marks in the chat if you have attempted all the 15 questions. I'll be happy to, and you can give me your feedback as well.
Hello, ma'am.
Yes.
I want that, you mentioned that the application of quantum information and technologies in financial sector.
Yes.
Hello.
Yeah, it's your.
So
I'm not
I
able
want
to hear it properly. Yeah.
I'm asking that I was asking that you mentioned that the application of quantum systems in financial sector. So I wanted to ask that whether like it has the potential for improvement than the existing operating system which the BlackRock company, the investment manager company uses, the Aladdin software. Like, does it have more potential than the Aladdin?
Okay, so what I understand it, you want to know whether the application which we performed performs better than what it is already existing. Am I correct?
Yes.
Okay,
yes.
So this I can tell you that I don't have an answer to it, because the results in the table, and we are also working on it now, it is always the same. It is coming the same as what the classical is showing me. Now, there are different classical algorithms, state-of-art algorithms to perform it, but so it's very difficult to say that whether it will be better than what we have now. And I clearly think that it will not be better. What we are trying to do is to see whether the algorithm gives the same result, at least what we already have, right? The advantage of quantum will come in when we'll explore the application vertically, like you want to have more, and horizontally. So if you want to have more stocks in the portfolio, or you have more portfolios, so the advantage comes in there, because that gives you, when the classical systems becomes computational intense, they get saturated. So that is where the advantage comes. Today we have to understand whether whether we are approaching this problem. When we have a problem, we are taking the quantum variational algorithms, QAOA or VQE, or maybe a photonic based maybe walk. all these should give you the results, at least what you are getting right now. That we have seen. Now we are the advantage is where you want to explore more, you want speed, then you need a quantum hardware.
Okay, ma'am.
There is a next question. What kind of qubits are being planned to be used for the 20 to 50 qubit quantum computer at CDAC Pune?
Okay, so I think it will be more superconducting based qubit. So we are exploring the market at present. And what looks likely is superconducting qubits, transmon qubits.
Okay. Can we describe the next question? Can we describe the state of HV in terms of Pauli spin matrices?
So right now, again, if I heard you correctly, that we are still exploring. So we do not know which is going to scale today. And even, that, for example, the Microsoft's topological qubit, with lesser number of qubit, if it has lesser noise, then maybe that is going to perform better. Or we can explore more qubits than the other technology. So it's very difficult to comment right now that which one would we see as something which is more, will be good to hold on. I don't have an answer to that.
Any other questions?
I have a stop at 12 o'clock. So I'll be very happy to take questions even by mail or,
Yes, sure. So with that, let us thank Dr. Anindita for a wonderful talk, and also how CDAC is spearheading and bringing the collaboration with the academia, industry, and driving those on the front of government aspects, and with various topics that they are working that she have touched upon. With that, we would like to thank Dr. Anindita on behalf of the organizing team for this wonderful talk.
Thank you. Thank you.
So probably with that, we have also, okay. So with that also, we have our next speaker for this workshop in the